system. If you have two stars that are really close together, one of them goes supernova, how can you guarantee the other star is going to survive in the first place to produce another neutron star, let's say? If you have these two neutron stars, and maybe one of them is far enough away that it survived, well then, that's going to take a long time for the two to actually merge. So how do you make sure that they merge before the universe has ended, let's say? So these are all questions that require a lot of physics and a lot of different considerations to go into. So to start off, I just thought this was pretty. So here, I guess we can turn off the lights because all I have are slides. How do you turn off the lights? What am I looking at? Ah, okay. Are these? Wait, front. That's good enough, I think. All right. So here we have a flower. A flower as seen in sort of by different kinds of vision. I mean, humans, we see visible. Bees and birds and other animals, they actually see UV as well. And if you notice, at the very top, so top left, there's human vision. That's what we see. The other three panels here include UV vision, right? And so you start to see new patterns form that if you were just looking at one wavelength or one frequency or one frequency band, you wouldn't have noticed. Something happens when we look at the galaxy. So here we're looking at the galaxy, top left is optical, so we see the stars. This is kind of what you might see with your eye or a good telescope in your backyard if you are lucky enough to be somewhere without a lot of light pollution. And then you also have in the infrared, you get a lot of sort of emission from dust and sort of diffuse matter, other material in the galaxy. And then in X-rays and gamma rays, you start to see really bright point sources that are both in the galaxy and outside of the galaxy. And you can do the same thing if you look at the sun. If you look at the sun at wavelengths, you start to see different features of the sun. So, I mean, with our normal eyes, we shouldn't look directly at the sun, but if you have a nice telescope that is able to look at the sun at different frequencies or different wavelengths, you'll notice that maybe at longer wavelengths, like the sort of second row, the yellow and the green, it's pretty stable, right? There's not much going on. And then you get to shorter wavelengths, higher temperatures, and you start to see a lot of activity that, again, you wouldn't have seen if you only looked at the longer wavelengths. So going back a little bit, all right, so we have the sun. How do we get there? What's going to happen? So the sun right now is sort of in the middle of its lifetime. And at the very end, I don't remember what the sun's lifetime is, like 1 billion years or something. At the very end, it's just going to turn into a white dwarf. That's just how it's going to die as. We turn back time, about 4.6 billion years ago, where did the sun come from? It came from just a gas cloud. It came from a gas cloud and density perturbations and just a region that was dense enough that it managed to collapse under its own gravity. And at some point it started to produce, things started heating up and reactions started to occur, and then what we have left over is the sun and also other stars. If we zoom out even further, the gas cloud is part of the Milky Way galaxy, which was sort of created or formed or however you want to, it was came together about 13.5 billion years ago. And before that, if we zoom out even further, nope, wrong way. We zoom out even further, you have the Big Bang. So at the far left, this is sort of standard cosmology, right? And sort of like a couple of slides. So on the far left, what do you have here? You have just some extremely energetic sort of beginning of the universe, right? And then very beginning, very fast, things were, let's say, inflation happened, so things were expanding very rapidly, and in the very beginning, things were so dense and so hot that photons couldn't escape. So they were kind of stuck in this pattern. And sort of like in a GRB jet, as things propagated and things expanded, at some point it became, the density dropped enough and the temperature dropped enough that the photons could then escape. And that, there was a moment, there was sort of a surface of last scattering, right? So there was a time when the photons couldn't escape, and then all of a sudden they could. And so when they could escape, they just went off into the rest of the universe, and the universe just kept on expanding. And so if we look back, we can actually measure that surface of last scattering, what we call the cosmic microwave background radiation. So today, this is sort of standard cosmology, is that the universe is made up of radiation. It's made up of baryonic matter, so the normal matter that we encounter every day. It's made up of dark matter. It's made up of dark energy. The dark matter and the dark energy are sort of still question marks. And the behavior, well, is the universe expanding, contracting, what's going on? the behavior is governed by it's just the physics. So radiation pressure is just going to cause things to expand. The baryonic matter will sometimes cause things to expand because gravity attracts. It will also sometimes cause things it will sometimes cause things to contract because of gravity. It will also sometimes cause things to expand because you have electromagnetic forces and things like that. There's also dark matter, which only causes things to contract. In sort of standard cosmology, it only interacts gravitationally. And then you have dark energy, which falls out of the math, and then this basically is just a way of saying there's something else that's causing the universe to expand. And so now the question is, well, how do we know this, right? You might have seen this before. The universe is composed of these things, and it's however much percent of this and this. Well, how do we actually know this? So what you're seeing here is the cosmic microwave background a map of the cosmic microwave backgrounds. And one thing that people will say is, they'll tell you this plot and say, oh, look how uniform things are. And you look at this, it's like, well, I mean, it's not that uniform. There are little bumps and wiggles, right? There are a lot of little overdensities and underdensities. But the deviations from uniformity, how much they deviate from being completely flat and completely uniform, is less than 1 in 10 to the negative 5. So really uniform. But if you closely, you can still see, humans are really good at picking out patterns with our eyes, right? But you might be able to see, you could convince yourself there's some structure maybe. So you could also do that mathematically. What you can do, you can say, well, how much structure is there at, let's say if I take this, 90-degree patch in the sky, how much structure is there compared to this 90-degree patch in the sky, compared to this 90-degree patch in the sky? And then what if I do it in smaller patches? What if I take 1-degree patches or like half-a-degree patches? How much structure is there overall in patches of this size? And when you do that, you see that this whole, what's something that looked uniform and is fairly uniform, it actually has this sort of structure. And so what you're seeing up here, the vertical axis is just the fluctuation, the temperature fluctuation. So this is how much it's deviating from uniformity. On the horizontal axis, I think the lower axis is easier to understand. This is the angular scale. So this is, so an angular scale of 1 degree is saying two regions of space that are separated by 1 degree in the sky. If I look at just that 1 degree patch, how much does it deviate from uniformity? And it turns out, if you look at it, let's see, everything that's smaller than 1 degree, these are things that if you go back in time, they were physically coupled, right? So they are separated by less than the light travel time based on the age of the universe. So everything on this right side was physically coupled. Everything on the left side was not physically coupled. The height of the position of the first peak tells you whether it's at 1 degree or left or the right. It tells you whether the universe is sort of negatively curved, positively curved, or whether it's flat. The height of the second peak tells you the amount of baryonic matter. The height of the third peak tells you the amount of dark matter. And so when people say, well, the universe is this percent baryonic matter, is percent dark matter, it comes from taking the data and then fitting it with the model. All right, so we have the universe, and we have some fluctuations, density fluctuations in the universe. How do we get to galaxies and stars? What we get is, we get density perturbations leading to these overdense regions. The overdense regions collapse, and it's sort of this runaway collapse where under gravitational collapse, you start to see these large-scale structures and these filaments grow, right? You start to see these strands, and you start to see these bright spots, basically. And these bright spots are just over regions. And if we zoom in on a portion of the box, and these are just some simulations, you zoom in on the portion of the box. So these are, I think, just actually galaxies. So these are really, let's see. Yeah, so this is showing the motion of individual galaxies orbiting each other, or over densities. This might be dark matter over densities, and each of these dark matter over densities houses a galaxy. Zoom in even further, you have dense gas clouds. And then same process, right? You have overdensities, and then the overdensities collapse and then draw in more material, and everything collapses into them. And then you get formation, so you get these dense gas clouds, and then you get formation of stars. And this is another simulation where they're just showing that stars are forming in this sort of whirlpool, and they're some of them are, have enough energy to shoot off, and some of them are just stuck in an orbit for a little bit, and they're all interacting with each other. That's a pretty thing. All right, I'm done. All right, so we have a gas cloud, and out of it come stars. Some of the stars are the size of the sun or the mass of the sun. Some of them are much smaller. Some of them are much bigger. 80 to 90% of a star's lifetime is in basically hydrostatic thermodynamic equilibrium. Everything is very stable. Most of the time, everything is very stable. The star can basically just be defined by things like its temperature. There's not much, there's individual there's small fluctuations within the star. There's no sort of really, there's nothing very complicated there, zeroth order. So what defines how a star evolves? Well, the star, it's sort of just balancing forces, right? You have the self-gravity of the matter in the star, and the more mass of the star, the more self-gravity it's the inner layers are going to be affected by. And then you have the outward pressures like radiation pressure and gas pressure, or sort of fermion degeneracy pressure, because you have all these electrons and you have these protons and neutrons, and they can't really occupy the same level, so at some point, or the same state. So at some point, you're going to hit that pressure. Usually what happens before that is affected by the radiation pressure, which goes as the temperature to the fourth. So just increasing the temperature by a little bit increases the radiation a lot. So this is sort of a very simplified overview of the life of a sun-like star. So the star, for about 80% of its life, is called a main sequence star. And on the main sequence, it's being pretty boring. It starts off composed of, let's say, hydrogen. If it's composed of hydrogen, it's going to try to collapse under self-gravity, right? It tries to collapse, and at some point, it starts to heat up enough that the core starts to fuse hydrogen into helium. In order to have these fusion reactions, you have to have successively higher and higher temperatures to overcome, the Coulomb potential that's forcing these charged nuclei apart. So you have higher and higher temperatures. It starts burning hydrogen to helium at the core, and then at some point, it runs out of hydrogen at the core, right? The temperatures, you can't really compress more because there's not enough mass on the outer layers of the star, because it's only one solar mass. When that happens, the outer layers start to expand. There's nothing really keeping them together anymore. The outer layers start to expand. The star becomes a red giant. This is going to be the future of our sun. I think when our sun becomes the red giant, the outer envelopes are going to go past Mars or something like that, engulf the Earth, everything, yada, yada, yada. So the outer layers start to expand. At some point, the outer layers are expanding, and they're getting farther and farther away, and so you might lose some mass. You're going to lose some mass from the outside because it's not really, it's not very close anymore to the gravitational potential of the sun, or of the star. And then the core, however, the outer layers are expanding and flying away. The core is still contracting at that time because the core still feels all the gravity of everything around it, so starting to contract. And then at some point, the temperatures get hot enough to burn helium into carbon and oxygen in the core. And then for a star the mass of the sun, stops. The contraction doesn't get hot enough, or the contractions can't make things hot enough to burn heavier elements. So it kind of stops at carbon and oxygen, and then it can't do anything else. So then the outer layers just kind of float off again. Well, not quite that. A little bit more complicated. But basically, what's left behind is you get just a carbon-oxygen core. It's a white dwarf. Call it that because it's small and because it's pretty hot. And then at some point, it's just going to radiate away because it's basically a dead star at that point. It's away, you don't have much left, and then it becomes eventually maybe a brown dwarf or the black dwarf. And then at some point, we can't observe it anymore. So that's the life of a sun-like star. What's more interesting is the life of massive stars. So these are stars that are hand-wavy, greater than maybe 10 times the mass of the sun. So if anyone's not familiar, this is kind of anytime you see a subscript of a circle with the dot in the middle, that just means sun. So these are heavier than about 10 times the mass of the sun. And these stars start out very similar. They're on the main sequence. They're burning hydrogen into helium. Because the stars have more mass, and as they contract, they convert that gravitational energy, let's say, into heat, roughly speaking. And so when that happens, that just means that massive stars can get hotter, much more quickly. So that means that this fusion of hydrogen into helium, it's happen much more rapidly. So massive stars evolve much more rapidly than lower mass stars do. So the massive star Similar way, it's on the main, or similar sort of situation, it's on the main sequence. It runs out of hydrogen at the core, outer layers expand, you have a red supergiant. The massive star then kind of undergoes this contraction and expansion multiple times, right? You get hydrogen to helium, helium into carbon oxygen into heavier and heavier elements. So you start to build up heavier and heavier elements. You still have your core of the heaviest element, because that's where it's hottest, and then you have these surrounding sort of onion-like layers of lighter and lighter elements. And then at some point, what happens is you hit the core, it hits iron. It fuses things into iron. And once that happens, it can't fuse things anymore. And the outer layers then, there's nothing holding the star up anymore. There's nothing going on. There's no more heat rate or gas pressure that's pushing things out. And so the outer layers just collapse really quickly. They collapse really quickly. They rebound off of the inner layers, and there's sort of all this also release of neutrinos and other photons and things like that. And they just blow off as a supernova. So in all of these, a star is stable if the inward gravitational pressure is sort of balanced by the outward radiation and gas pressures. The radiation and gas pressures, these are from fusion reactions, right? So how, what is keeping a star upright, or not upright, what is keeping a star from collapsing? It's fusion. It's fusion at the core into heavier and heavier elements. For a while, that fusion is energetically favorable. The problem is, once you hit iron, that's no longer true. So what you see here in the vertical axis, the average binding energy per nucleon, or how much energy it takes, how much energy there is in keeping basically the nucleus together. On the horizontal axis, this is the number of nucleons in the nucleus. This is just going up the periodic table. And then you see iron is at this one peak. And so if you go heavier than iron, if you form something heavier than iron, you try to fuse that just by simple, straightforward fusion together, it's going to want to undergo fission. It's going to want to split again. And so at that point, you can't really get more energy out of the star by fusing. And so if you can't get energy out, the star just supernova. So what's left at the end of the supernova? That really depends on the mass of the core. If the core mass is lower than around 2 solar masses, what you get is the core ends up being supported by neutron degeneracy pressure. So you get just basically a ball of neutrons, zeroth order, you get a ball of neutrons. And the object, what you're left with, is a neutron star. If the core mass is greater than about 2 solar masses, then the neutron degeneracy pressure can no longer overcome the gravitational collapse, and the core collapses even further into a black hole. There are also possibilities where scenarios where the star is destroyed entirely, or the core is destroyed entirely, but in that case, that's not very interesting to gravitational waves, or binary mergers at least. So I'm going to focus on these two. So now we know how, roughly speaking, how to get one compact object. How do you get 2 compact objects? How do you get them to orbit each other? Do the stars themselves have to have been orbiting each other, or can you get a neutron star and a black hole by themselves to later capture each other and orbit each other? How do you get them to merge? How do you get them to merge in a reasonable amount of time? And basically that means, how do we get here? So what you're seeing here is a figure called masses in the stellar graveyard. What this is showing is that the top circles are black holes. The blue circles at the very top are the LIGO detector, or the gravitational wave detected black holes. So these are the ones that were in binary mergers. And so that's why you can see that there's always 2 and then arrows pointing off to a third. So those are just the initial black holes and the one final black hole. Underneath that, it's a little bit hard to see because it's dark, but it's in dark purple, there are electromagnetically detected black holes, which I'll get to in a second. The electromagnetically detected black holes, these are ones that we knew of. These are basically ones in our galaxy. We knew about them before gravitational wave detections. But you can see that the populations are a little bit different, right? The LIGO, I stopped saying LIGO. So the gravitational wave detected black holes are in general more massive than the electromagnetically detected black holes. And then at the very bottom, you have the neutron stars. You have most of them being electromagnetically detected, and then you have the one binary neutron star merger producing something that's a question mark. Yep. Yep. That's an excellent question. LIGO is working on, or people are working on right now. So the question was, why does there seem to be a gap between, say, 2 and 5 solar masses? What's in that gap? Is this an actual physical gap? Is this a gap based on physics, right? Or is this a gap that's just observational? It's unclear right now what it is. One thing you'll notice is that what's left behind after the post-merger remnant for the binary neutron star is right in the middle of that gap. So that was part of the problem of what was left over after the binary neutron star merger, because there's nothing that tells us that in that gap it has to be neutron stars, or in that gap it has to be black holes. I think it's most likely going to be some sort of observational bias. So so neutron stars can only get so heavy. Black holes, right? So you would think that there should be black holes that are, a couple of solar masses and things like that. But this gets into how do we detect black holes, or electromagnetically detected black holes. How do we detect these black holes? This purple layer of black holes is when they somehow emit electromagnetically. Well, how do black holes emit electromagnetically? They have to be accreting material, right? So they have to be accreting something. The more massive the black hole, the more it can accrete, the faster the accretion rate is, and then the brighter the emission is. And so it could just be, in that case, a selection effect, because if black holes are less massive, then they're not going to be as bright if they are accreting, and then we're not going to observe them. It's also possible that there's something inherently different, because maybe if a star would have otherwise produced like a 3 or 4 solar black hole, maybe this is not a stable kind of evolution, I guess. If you have, in order for things to accrete, all of these electromagnetically detected black holes are in binaries with main sequence or with normal stars. And so it's possible that maybe there's some reason why you can't have a stable binary with a 3 solar mass black hole and a normal star. But that's unclear, and that's sort of one of the questions that people are still trying to solve today. Yes, so now the first question is, how do we detect these electromagnetically detected black holes? Going back a little bit, if you have 2 stars that are orbiting each other, they both have some sort of gravitational potential. And if you draw out the gravitational potential, you find that there's a point in the middle where, they both have these regions, what's called a Roche lobe, where anything within this region around that star, any material that's within this region is going to be gravitationally bound to that star. So at some point it's going to orbit in, or the orbit is still bound to the star. Anything outside of that will float away. Well, roughly speaking, will float away into infinity. There's a point in the middle, right? Because both stars have their gravitational attraction or gravitational potential wells, and so there's a point right in the middle where you can sort of transfer material from one star to the other. Depending on what we say stars have filled or not filled their Roche lobes, right? So depending on whether a star has filled its Roche lobe, which just means that material from the star, maybe the outer layers because the star has expanded, just means material from the star has filled this region and could start to either evaporate out or could start to transfer onto the other star. So you could have completely detached binaries where neither of them has filled its Roche lobe and they're all just hanging, they're just far apart. You could have a semi-detached binary where one has filled its Roche lobe, or you can have a contact binary, both have filled Roche lobes. This matters because with all of these, you could have mass transfer. So with mass transfer, if you have a detached binary, in all these scenarios, you could have mass transfer. If stars that are far apart and that with no materials that have not filled their Roche lobes, you still have these things called stellar winds. What's a stellar wind? So the stellar wind is basically just sort of rapid driving off of the outer material of the star, right? Because the star is producing radiation. The radiation is bombarding sort of all the material. It's hitting at the material, and so you still have the outer material kind of blowing off, and so that's what we call the stellar wind. You could have, in a detached binary, you could still have transfer with the stellar wind. That's sort of a slower mass transfer. They're farther apart, and the wind is not as strong. Detached binary, you could have stellar wind, you could also have Roche lobe overflow, and in this case, normally you have the mass transfer is usually a little bit faster. In a contact binary, you have basically there's so much material around, you've overfilled the Roche lobe, at this point, you only have basically one envelope of material surrounding both stars. And then you have this sort of what we call common envelope evolution. And this matters because this will really change the evolution of the individual stars as the binary. And a similar thing can happen if you have a compact object, right? So if you have a compact stars and one of them goes supernova first, usually the more massive one, because more massive stars evolve quicker. One of them goes supernova first, and you're left with a black hole, let's say. The second one will still be affecting the first one. Is there a question?
How can the supernova survive with the supernova from the other?
That is something that's an entire research field, basically. Let's see. Yeah, I don't have a good answer for that. That's basically an entire research field. There's a lot of studies on how to do this. And I think with a lot of simulations, I think it's, if things are enough at that too close and they're far away enough, then it'll survive. So I'm sorry that wasn't a very satisfying answer. So all of the electromagnetically detected black holes we've detected so far are accreting material from a companion. Oh, the interesting thing, actually, this is fun. So if we electromagnetically detect black holes, they have to be accreting material. So for the most part, so far, we've only detected them if they're in binaries with companions that are transferring mass onto them. Theoretically, they're moving through the interstellar medium. Theoretically, if you have a black hole moving through the interstellar medium, if it's moving through something dense enough and at the right velocity and everything, you could still get accretion onto that black hole. So theoretically, when we have in the future X-ray detectors that are sensitive enough, and the proper kinds of X-ray detectors, we could possibly identify isolated black holes just because they're emitting X-rays very dimly as they go through and accrete the interstellar medium. And in the future, other ways we could maybe detect isolated black holes in the galaxy is looking for evidence of lensing, right? So you might have heard of lensing from massive black holes or from other galaxies, right? Basically the whole thing where you have, let's say you have a bright event over here. You have a bright event in the background, and there's a really dense object in the foreground. Could be, just a supermassive black hole or another galaxy. So that means that the light that's traveling to us from the event in the background is affected by the gravitational potential of the light of the object in the foreground, or the dense object in the foreground. And so what happens is a lot of times you get this sort of ring, right? It comes over here, and some of the light gets bent this way, some of it gets bent this way, some of it gets bent this way. So what you see is sometimes if you look at these images, you see the same object, exactly the same object at different parts in this ring around the sky. And so we have observed gravitational lensing with supermassive black holes, and theoretically in the future we might also be able to detect it, or we should be able to detect it with stellar mass black holes in our own galaxy as well. So that's kind of fun. Going back to X-ray binaries. So far, all the black holes we know of electromagnetically are in binary orbits with companions. And we call them either low mass X-ray binaries or high mass X-ray binaries. Low versus high mass just means the mass of the companion. And let's see, not all X-ray binaries have to have a black hole as their compact object, but in this case, I think I'm not going to focus on only black holes. So the compact object could be a black hole or a neutron star. So here is an example of a high-mass X-ray binary called Cygnus X1. And I'm just going to go over this as an example of how do we know what the mass of the black hole is? How do we actually know what the mass turns out to be? So Cygnus X1, what's happening is there's a black hole. We know it's about 15 solar masses. It's in an orbit with a blue supergiant. So this is around 20 times the mass of the mass of the sun. So it's just really high temperature, and it's losing a lot of material. That material is leaving its own Roche lobe, and it's going into the Roche lobe of the black hole, and it's accretion disk to form around the black hole. We already know you have a black hole, an accretion disk. That black hole is going to emit something. It's going to emit radiation. What this black hole emits in particular, it emits X-rays from that hot accretion disk. So X-rays come from that hot accretion disk, and then it also emits a radio jet. The radio jet, so this is similar to GRBs, right? Whereas it runs into the interstellar medium, then you have the afterglow emission as it fades and things like that. Something similar happens in Cygnus X1 and other X-ray binaries where you have this jet, and the jet plows into the surrounding medium, and then because it heats up that medium and accelerates particles, and the particles decelerate, you have synchrotron form of optical and radio emission. And they orbit each other every 5.5 days or so. And these are these are observations of Cygnus X1, or that whole region, the radio and the optical. Left-hand side, we have the radio. Right-hand side, we have the optical. On the left-hand side, starting with the radio, what you're seeing at the very bottom, that sort of inset and the kind of bright circle at the bottom, that's the collimated jet. That's just the edge of the jet that we see. When you see the jet, so what's happening is you have this jet, and at some point, so that's the hottest part of the jet, and then at some point as it goes out, it gets cooler and cooler, it expands and it slows down, and then you see this material, this sort of oval material at the very top, and this is just the shocked material that's slowly expanding. So this is what's known as the what we have is the synchrotron lobe. So there's all the synchrotron emission inside, and then at the very end you have bremsstrahlung gas, and then you have this shape at the very top, and then you can also see it in optical where you have the bright Cygnus X1. So that's from the black hole itself, and then you can see in optical also kind of this lobe up top. So now the question is, how do we actually know, right? How do we know it's a 15 solar mass black hole? How do we know what the companion is? How do we know what's going on? And what you do is you take the best data you can, and you have your model of what the brightness, how the brightness should fluctuate, or how it should behave over the course of an orbit. You fit all your parameters, and from there, you figure out the mass of the black hole. So what you're seeing on the right-hand side, the first 3 rows, these are just the brightnesses and different frequencies, basically, or the brightnesses at different optical bands. And what you're seeing is how the brightness changes over one orbit. Because what's happening is sometimes sometimes they get closer, and then you get extra material, and then it brightens, it gets farther away, and then there's less material, and then it dims again. And so by fitting all of these parameters, you end up, what you get is the one that fits the best is going to be one that is gives you a 15 solar mass black hole. That's the sort of thing that people do in order to figure out how massive black holes are in these electromagnetically detected black holes, or for these black holes. You can also have low mass X-ray binaries. An example, Scorpius X1. I want to talk a little bit more about Scorpius X1 tomorrow or Friday. I don't remember exactly what. But in this scenario, what you have is a neutron star, and you have what's called an evolved subgiant. So this is a star that's it's very similar to, it's lighter than the sun. It's lighter than the sun, but it's kind of puffed out a little. These two are orbiting each other once every day or so. And then the interesting thing about Scorpius X1 and other low mass X-ray binaries and other binaries with a neutron star, so you have this accretion disk, and in a black hole, you get the accretion disk, and then the black hole accretes the material, and you get a jet, and you get emission. With a neutron star, you have this strong magnetic field. And so the accretion disk, or the accreted matter, hangs out around the neutron star, and then it kind of goes along the magnetic field lines. It's transferred along the magnetic field lines, and what you end up with are 2 hot spots on the neutron star. And these hot spots, so you get increase in temperature on this neutron star, it emits X-rays. You can also get, because this is where the material is landing, so you can also get a buildup of material. So this is a mechanism where you might asymmetric neutron stars. This is interesting because slightly asymmetric neutron stars rotating around, that's just a changing mass quadrupole moment that's accelerating. And so from that, you could get gravitational waves. But I'm going to talk about this more tomorrow or Friday. I don't remember which one. So we know how we got to the electromagnetically detected black holes. How do we get to the LIGO detected ones? What are some possible mechanisms for how we get these black holes to form, how we get them to form in pairs, how we get them to merge? Because with the electromagnetically detected black holes, these are in more or less stable orbits. These are going to take a long time for most of these are never going to merge, or at least we're never going to observe them merging. They're never going to merge, they're just going to hang out. That's relatively easy to form in a system like that. It's a lot harder to form a system with the gravitationally detected black holes in order to get them to merge within a Hubble time. So the overall scheme of trying to answer this question, what you do is you simulate tons of different systems. You take all these systems and you say, what are the masses? What are the metallicities? What are the initial separations? What are the initial lepticities? And a lot of other things. Metallicity. We talked a little bit about metallicity yesterday. Why does metallicity matter? So reminder, in astronomy, anything that is heavier than helium is a metal. So why does metallicity matter? What happens is if you have, and where does this higher metal come from, right? Because I was saying stars start out as high and then they go to helium and yada, yada, yada. But sometimes stars start out with a higher concentration or with some concentration of metals. And how does that happen? I mean, it's just because, the star is made up of gas and gaseous material. That material, so what you have is initially the very beginning of the universe, it was all hydrogen, and then at some point, some stars went supernova, and then when a star goes supernova, it seeds the surrounding region with the heavy materials that it's created. And so new stars formed out of that sort of recycled material are going to just start off with higher metallicity. So that's it. Why does metallicity matter? Metallicity matters because with higher metallicity, you're going to lose more material. The stellar winds are going to be higher. You're going to lose more material. By the time the star dies, it's going to be, on average, much less massive. Why does this happen? So imagine what's happening is, right, you have the stellar winds happen because there's a lot of radiation created at the center, a lot of heat, a lot of temperature, or a very high temperature. Photons go out, and that pushes sort of the outer material or the outer layers out. If you have metals in there, you have metals that are going to absorb the photons. If you have metal that's going to absorb the photons, it's going to get heated up, and it's going to leave that much faster because you've all of a sudden just increased the energy of these elements now, or of these nuclei. And so the more massive, on average, the more massive a star is, the more mass it will lose. So what you have all of these different systems, these different binaries, you give them different properties and stuff, evolve forward in time. You say, all right, the more you have some physical model for how fast stars evolve, and then you have some model for what type of supernova they undergo, or like what happens when close, or what happens with the mass overflow and things like that. And then at the end, you see which systems produce one similar to the one you want. So if you have these two LIGO detected black holes, these are 35, 40 solar masses, you start off with a whole bunch of different systems over here, and you see what are the systems that produce this final black holes that are similar to 35 or 40 solar masses. What do they have in common? So how do you get these stars to form in the first place? The main thing is that a sizable fraction of stars are actually formed in binaries. Somewhere around order of magnitude, half of stars are formed in binaries. Remember that simulation I had at the beginning that was the red one, and then you had all these stars forming out of the swirling gas? How many stars were formed out of one ball of swirling gas? And so stars are going to stay in binaries, right? They're going to stay gravitationally bound to each other. And I don't remember what the simulation is. Is this actually a simulation? What did I do? Nope. Yeah, okay, yes, it's going forward in time. Oh, it's too dark to see. Here we go. Yeah, so, this is just density and things like that. So what's changing here is they're seeing what the effect of the magnetic field is. So here it's the magnetic field, I believe, in the surrounding material. These are very weak magnetic fields. But what's going on is that just showing that depending on things like, the magnetic field, the density, and things like that, the initial conditions, you can get either, individual binaries forming, you can get pairs of binaries, you can get binaries, you can get individual stars. You can get all of these complex systems just by changing the magnetic field slightly. That's the only way to get stars formed in binaries, however. If you have, if you look at, if you have a really dense gas cloud that could form a lot of stars, then you have a region with a lot of stars that are orbiting each other. Some stars might have started out isolated, but then they get close enough, and then maybe they're captured by a more massive star. Maybe you have a three-body interaction, and then what ends up happening is that two of them end up gravitationally bound to each other, and the other would have shot out into space. So there are multiple ways to get binaries, and it turns out it's much easier to get a binary than one might think. So the question of initial separation is so this is a tricky one that has to be overcome, right? So if the binary starts out with a really large separation, both objects are going to survive just fine, but they're both going to evolve on their own, so they're both going to go supernova on their own, and then they're too far away. They're never going to merge. And so the naive thing to do would be to put them really close together at formation. They're really close together at formation. The more massive one is going to expand. It's going to either destroy the secondary one, or it's going to accelerate the evolution of the secondary one. And then at that point, the objects will have already merged today, and we wouldn't have detected them. And so there has to be something that lets the objects merge at a rate that is compatible, I guess, with what we're observing today. And this is going back to mass transfer. So for the first two scenarios where you only have one object overfilling its Roche lobe, so what I was saying is you kind of have this sort of slow, medium mass transfer. That's also known as sort of stable mass transfer. Stable mass transfer simply means that the recipient star, the recipient, is to accept all of that extra mass. And it's stable, and it sort of accepts the mass goes on, and then just accretes onto that star, let's say, and then becomes part of the star. In that case, what ends up happening is, right, so one thing that could happen is that the two masses of the stars could switch. The heavier one could become the lighter one could become the heavier one, or they could just equalize. And so when that happens, the separation can widen. On the other hand, if you have unstable mass transfer, so you have a really high mass transfer rate, and the secondary now can no longer accept this mass or this material onto itself, what happens is you get common envelope evolution. With the two stars being in a common envelope, all of a sudden you have so much more friction. You have all this friction, you have all the energy losses due to friction, that will put your two stars together very quickly. And quickly enough, and it turns out that common envelope evolution is basically what you need for most, if not all, of the gravitational wave detected black holes to be compatible with the rates that we observe today. This is just, I guess the plot's not that important. This is just showing that the stellar lifetime versus mass. So vertical axis is the log of the lifetime, and the horizontal axis of is the mass of the object. This is just saying that more massive stars will evolve much more rapidly. So in a binary system, this means that the heavier star will evolve faster than the lighter star. By evolve, I mean it will expand and then contract and expand, contract, and at some point supernova. And so when it goes supernova, there's some other effects you have to take into account. So what I'm showing here is a map of pulsars. So pulsars are neutron stars with large enough magnetic fields that they're emitting, that they are launching sort of these jets that have radio emission, and this is how we detect most neutron stars that we know about, this is how we've detected most neutron stars today, is that they have these jets, and every time, it's sort of like the lighthouse model. Every time the jet points at us, we see a bright flash, or we see an excess in radio, and sometimes also in gamma rays, X-rays, that sort of thing. So this is a map of pulsars, and what you're seeing here is just, longitude, latitude, and the Milky Way, the Milky Way galaxy is the strip in the middle, which is why there's a density, there's a lot of neutron stars right in the middle, but there's also a lot of neutron stars at high and low latitudes, so really far away from the disk of the galaxy. So these neutron stars formed in supernovae, so they came from regular stars. The neutron stars came from regular stars. We basically never see regular, main sequence or regular stars that are that high above the Milky Way galaxy, right? They're all in the disk. They're all in the disk. They're not very far off. But we do see neutron stars there, and this is going back to the supernova case. With the supernova being so energetic that at some point, if you have even a little bit of asymmetry, that little bit of asymmetry is going to kick the neutron star really far, really fast. And neutron star kicks, supernova, the natal kicks, could be as high as, I think the observed ones could be, 800 kilometers per second, almost 1,000 kilometers per second. And this is only what we have observed so far. There could be other ones that are even faster. So, because when you have a supernova going off, and then you end up with a neutron star, that star could get kicked out. That also is an effect you have to take into account. So in some percentage, some fraction of your binaries, when one of them goes supernova, that one is going to get kicked out, and that could break your binary entirely. Or if it goes supernova in the other direction, this is interesting. When you go supernova in the other direction, if you have a neutron star and it goes supernova and gets kicked towards the companion, it could actually, theoretically, it could sort of slingshot out the companion's core, and it could replace that companion. It could actually replace the core. And so theoretically, it's a theoretical object, but there's some There's some evidence that there might have observed one already. It's a little unclear, but you could have things where you have a neutron star core and then a red giant envelope surrounding that. So so this is sort of one of the last few slides I want to talk about, actually. This is an example of what you get in the end of how to get a binary neutron star. This is a lot of words or a lot of short acronyms. So what you're seeing here is it goes from the top at time equals 0, and it goes to the bottom at however many mega years since it formed. This is a system where the metallicity up there is 0.01. I'm not sure if that means solar metallicity or just plain, or compared to solar metallicity, or just plain sort of, that's it, that's the metallicity. So, all right, so acronyms over here, letters. Z, metallicity. A, separation. R, the sun is just the solar radius. This is the way we normalize how far apart things are. E is the ellipticity deviation from circular orbits. Circular orbits will just evolve differently from elliptical orbits. So MS is the main sequence. So that's the hydrogen burning stage. That's the stable 80 or 90% of its life, the first 90% of its life. ZAMS, the zero age main sequence. This is how massive it is when it first starts out, first starts to burn hydrogen to helium, because like we said, as it continues, it might lose some of its mass and get lighter and lighter. HG, it's basically we get from the main sequence to the red giant, and there's sort of a gap in between. I mean, obviously the star has to evolve along there. It evolves very quickly, so we haven't observed it. But so that's just a star that's kind of starting to become red giant. Roche lobe overflow. I mean, so these are all sort of a lot of different terms. What basically happens is, and this is not saying that the binary neutron star merger came from this type of system, but this is a system that could have produced it and could have produced other neutron star mergers. What you start off with is stars that are around 9 or 8 solar masses. The more massive one fills its Roche lobe, right? So that's the second line over here. You see the HG donor, right? It's starting to become a red giant. Before it gets to the red giant stage, it's expanding enough that it overfills its Roche lobe, and you transfer mass onto the second one. So then the first one actually loses a lot of its mass, and it goes down to 2 solar masses, and the second one is much more massive now. It's 15 solar masses. The first one undergoes this type of supernova called electron capture supernova. The second one stays, hangs out, and then the second one expands now because it's really massive now. It expands, and it envelopes both the two objects in a common envelope. And you can see going from, at that stage, the separation goes from around 2,000 solar radii down to 46. So that really brings the two together a lot. And when that happens, you just wait for the second one to go core collapse supernova. You end up with 2 neutron stars. At some point, the neutron stars, if they're close enough, they're losing energy relatively rapidly due to gravitational waves. As they're losing energy, then the energy is radiated away, and then the orbit will slowly shrink. The orbit shrinks, and then it shrinks faster and faster, and then what you get is what we've detected last. That's just one example, and one set of, so there are a lot of people who work on these sort of evolution or stellar evolution codes and binary evolution codes. Another example on the right-hand side, so these are 2 channels that they propose could have caused this neutron star, or could have led to this neutron star. The first one is similar to the situation on the left. The second one is slightly different. In that case, you have these two, this unstable mass transfer earlier, and you have a common envelope forming earlier around 2 stars, and then they evolve kind of normally. The common scenario, the common feature in all of these is the common envelope evolution. How do you get a binary black hole? In some ways it's easier. You don't have to, it's easier to have a black hole survive an explosion in the neutron star. In some ways it's harder because binary black holes that have been detected by LIGO and Virgo are really massive, right? Going back to the plot I showed before, the masses in the stellar graveyard, the electromagnetically detected black holes stopped at around 20 solar masses. The ones detected by LIGO and Virgo go up to 40 solar masses, maybe 50 solar masses, a little bit clear. They're a lot heavier than the ones detected electromagnetically. So with heavier black holes, obviously you need to start out with a much heavier star. So you start off with a much heavier star, and in that case, things evolve much more rapidly. But again, you have to have this common envelope evolution. At some point, the common envelope, again, is what you need to get the two to be close enough to each other to merge within a Hubble time. And when I say things like a Hubble time, that just means the life of the universe. So then you get the question of how massive can these black holes actually be? If you have heavier and heavier stars, can you just get heavier and heavier black holes? And it's a little bit tricky. So a lot of this will depend on the metallicity, the initial metallicity of the star. Like I was saying, stars that are born higher metallicities with more metals are going to lose mass faster. And so a star with a high metallicity, at the end of its life, it's actually going to be less massive than a star with low metallicity. That means, so what you're seeing here are figures. These are just calculations. These are not, these are just calculations with some assumptions, but this is an example. So on the vertical axis, you have the black hole mass. On the horizontal axis, you have the initial mass of the star. So how heavy did the star start off as? With heavier stars, you can get heavier black holes. Sure. But what you'll notice is, so if you look at the red line, so that goes relatively straightforward, right? So that's the lowest metallicity, I guess. That's the lowest metallicity, and it's saying with a really low metallicity. So with with stars that don't have that much, don't have that many heavier elements, you can get black hole masses up to, let's say, 100 solar masses. You can get that. The problem is, if you look at this black line or not problem. The interesting thing is, if you look at this black line over here, that's the second line from the bottom. That's 100%. So that's exactly at the metallicity of the sun. So that's what I think the metallicity of our surrounding region is, because the sun shouldn't be anything special. So if you have a star that's born like the sun, as you get heavier and heavier, the initial star gets heavier and heavier. Sure, you can get heavier and heavier black hole masses, but it's really hard to get masses higher than 20 solar masses. So what does that mean? Does that mean that sun is special, or does it mean the galaxy is special? What's going on with these electromagnetically detected black holes that stop at 20 solar masses versus other black holes that stop at 40 solar masses? This could be a sign that what we're detecting are, because all the gravitational wave detected black holes are from outside our galaxy. This could be a sign that what we're detecting are black holes from galaxies that just are, for whatever reason, just have lower metallicities than our galaxy. Could be that maybe it took a while, maybe they're smaller, so it took a longer time for the galaxy to actually form, and so therefore it hasn't gone through as many cycles of supernovae and metallicity enrichment and things like that. Could also be that in our galaxy there might also be pockets that are this low metallicity, but we just haven't observed anything like that yet. So I think one of the last things I want to show, so these are the first three LIGO detections. So you have 150914 up there, where you have, I think, about 40 and 35 solar masses creating this black hole. You have 151012 over here, you have 151226 over here. Doesn't matter their phone numbers. What matters is that these are the three black holes I'm going to look at right now in particular, or the three systems I'm going to look at. These are some examples of how do you get these systems. So what you're seeing on the right here, let's look at the right first. Let's look at, what's the difference between these? Yeah, let's look at the bottom right. So what this is saying is, what you're seeing, these curved banana shapes, these are the contours. So these are the contours of what the final masses look like. So on the horizontal axis, you have the mass of the primary, again, just the heavier one. On the vertical axis, you have the mass of the secondary. And this contour with the orange just says that based on all the waveform modeling and the systems that best fit the data, that tells you that the final masses of the initial mass of the black holes must be somewhere along this line, or in this region. And similarly with the green and similarly with the blue. So these are just the three different events. What they did was then, so they took a lot of systems of stars, a lot of binary systems, and they said, what are the initial stellar masses that could produce the final masses that we think that LIGO observed? And so what you're seeing on the the bottom row, this is assuming a metallicity of 0.001, it's fairly low. Of the top row, it's a metallicity of 0.002, so twice as high. What you'll notice is that the top row seems to be missing blue dots, right? It's missing blue dots because it's missing, with this set of assumptions, with this metallicity, there are no stars that were able to produce black holes like the ones that are required by 150914. Just a reminder, 150914 was until very recently the one with the most massive initial black holes. And so what they were saying here is that you need sort of the lower metallicity in order to produce black holes like 150914, and this starts to maybe you can start to use this information, or maybe when you have more information with more black holes, you start to use this to try to say things about the galaxies that produce these black holes. This is my last slide. So these are some newly announced detections by LIGO and Virgo. These were, so this was announced, I think a week ago, maybe 2 weeks ago. This is on the archive. This is all public. This is all free if you want to take a look at. This is the whole thing where when you go back to your data with maybe better calibration and with sort of the noise, a lower noise floor, and if you slightly more complex waveforms, right? Because when you first detect the black holes, you want to do it quickly. You want to do it quickly so that you can get, the information out so that people can do the science on it. Then after a while, when you have a bit more time, you go back and you say, what about the more complex waveforms, the ones that, instead of having maybe ones that have precession, where the spins are changing a little bit as they start to merge, right? So that's going to change things up a little bit. When they did that, they found 4 more binary black hole events in all of 01 and 02. So advanced LIGO so far. What you're seeing here are figures for what they think the properties of the events are. So these are the 10 binary black hole mergers and the 1 binary neutron star merger. The top left, this is what the curves for the contours for the initial masses are. So whereas previously, let's see, 150914 is the dark blue solid line. And now you see there's this monster up here, that's this big purple thing, where you actually have even more massive initial masses. And that's, 170729. So this is a new one. And you could say, all right, well, if it was so massive, why didn't we detect it earlier? Well, we didn't detect it earlier because it was also really far away. Relatively far away. So if you look over here, let's see, where should we do? Yeah, we can do one of these. So if we look at the bottom right, this on the vertical axis, this is the chirp mass. Chirp mass is basically just a combination of the 2 masses. It's just a way of what is that word? Parameterizing the masses. It's just a way of it's just an easier way to define what happens to the waveform. So you have the chirp mass is a combination of the 2 solar mass, or the 2 stars' masses, or 2 black holes' masses, and then on the horizontal axis you have how far away it is from us. At the very bottom over here you have 170817. This is the binary neutron star merger, so it's the closest to. Understandably so, because these are less massive, and so therefore they radiate less energy, and therefore they have to be closer for us to detect them. And then you have this monster over here, 170729. Yes, the final mass or the chirp mass and all these masses are heavier for 170729, but overall it's farther away. What else do I want to show? Let's see. Yeah, bottom left is also a little interesting. So bottom left, the vertical axis is the distance, and the horizontal axis is the inclination angle. So gravitational waves, right? So you have 2 things orbiting, and it's emitting gravitational waves. You're going to get a stronger detection, right? The gravitational waves are going to be stronger if you're standing over here rather than over here, because they're radiating outward. And so as they're radiating, so this is what this is measuring. Actually, I don't know if I want to talk about this. It's just, this is just showing that there's a little bit of degeneracy, right? There's a little bit of a difference and a dip between the distance, how far it is away, because maybe something is, something's a little bit dimmer, maybe it's farther away, or maybe it's inclined at a slightly different angle. These are all the things that go into estimating the parameters of these systems. And I think that's all I have. Are there any questions? Yep, go ahead. X-ray binaries, so far we've only observed ones in the galaxy and possibly the Large Magellanic Cloud, so the 2 smaller kind of quasi-galaxies that are orbiting the Milky Way. We haven't observed X-ray binaries from outside the galaxy yet. It's just in general, stellar mass black holes you can only see within our galaxy. So all the so all the black holes from X-ray binaries so far have just been within our galaxy. Sorry? Let's see. So the question is, in general, how many parameters do you need to model the emission? It depends on how well you want to model the emission, or so with a stronger signal, like 15914 was a really strong signal, you could pick that out of the data by just having, roughly speaking, just sort of masses and I think, let's see, mass, distance, inclination, angle. It's sort of these, yeah, so sort of these parameters. I'm probably not the best person to ask that or to answer that. But if you check the papers, they will tell you. Sorry. Yeah. Sorry? Yeah, so the question is, how do you define a surface of the star? It depends on who you ask, right? Because going back to sort of the images of the sun, yeah, I mean, if it's all gases and stuff like that, right? I mean, it's kind of weird, right? Because you have the sun, and I mean, we see the sun, it's yellow, and so yellow is peaked at, I don't know, 500, yeah, like 500, Kelvin. And then you go farther out, you have the corona, so now it's whiter, or now it's a little bit bigger, and now it's like tens of thousands of Kelvin or something like that. It's a lot hotter now. That's why all of these are a little bit. So do you mean in general, or do you mean in like the X-ray binaries, or? Yeah, in general, it's basically you just sort of say, for one thing you could do, let's say, is you could, if you have a star over here, and you have your telescope that is okay to look at the sun, optical telescopes, don't stare at the sun directly. You have your telescope, you can move it across, right? So you can move your telescope across, and as you move it across, you can get, you take a snapshot of how much light is emitted in that, that you're observing in that patch. So when you're over here, you're not observing anything, or a little bit. When you're over here, you're observing a lot. And so then when you do that, you can get some sort of, you get some sort of distribution like this, right? When you get this distribution like this, then you could, at this point, you basically just say, I'm not sure exactly how stellar physicists do or stellar astronomers do it, but you can imagine saying, maybe you pick like 99% of your mass is contained within this radius, or of the luminosity or the brightness contained within this radius. So you might do something like that. So yeah, so the definition of the how big a star is or how wide a star is, it's going to be based on observations. Yeah, okay. Yeah, so the question, yeah. Why binary mergers in our galaxy, or in gravitational waves? I think it's probably, so there's two ways you can answer this. First off, it's probably a numbers game, right? There's a lot more black holes outside of our galaxy than within our galaxy. Obviously, within our galaxy, there's going to be, let's see, within our galaxy, closer, right? So the signals are going to be stronger. But remember, it takes a lot of sort of, you might say like, not all stars that form in binaries are going to form binary black holes that are going to merge within a Hubble time. And so it really just ends up becoming a numbers game of how do you get these systems to merge within a Hubble time. And again, just because there's just so many more black holes outside of our galaxy that really you're not going to expect necessarily to observe a gravitational wave merger in our galaxy unless you look for, I don't know, millennia or something like more than millennia. There's always the possibility, so that's the observational response. There's also the possibility that there's some sort of theoretical reason, astronomy reason why that doesn't. Because like we saw, you need this common envelope. You need the common envelope stage to get the two close enough to get them to merge. So it's possible that stars within our galaxy, for whatever reason, are just very unlikely to, binaries within our galaxy are just very unlikely to, form this common envelope. But there's a lot of, so that's unclear. It's a lot of speculation. Still have a little bit more time. Let me see. I can start to ramble about experiences of Fermi. Oh, this is a fun story. Yeah, okay, I have a fun story. So Fermi satellite, right? It's in the Earth. That's great. What happens is there's a lot of other things that are orbiting the Earth, and some of them are other satellites that can move out of the way, and some of them are not. So when you have a satellite in orbit, you have to care about space debris. There's not much to do about space debris, right? Things are moving really fast out there. What you do is for all of your satellites, you have to put you generally put some sort of shield over it, some sort of micrometeoroid shield that gets rid of the smallest particles, the dust particles. Because a tiny dust particle hurtling at thousands of kilometers per second could cause a lot of damage. So you need some kind of shielding for that. at one point, let's see, what should I say? At one point, a couple of years back, maybe 5, 6, 7 years back, so NASA tracks a lot of these large objects in orbit around the Earth, right? It tracks a lot of these large objects. The U.S. government, the military, tracks even more objects that they don't necessarily tell us about, and even smaller ones. I think they just have slightly better tracking systems. Anyway, so they normally don't tell us about it, but once in a while they'll say something. They'll ring up a satellite and say, hey, you guys are kind of going to be you're going to be sort of on a close impact. You might impact something else, basically. And so at one point, what was happening was, I actually don't remember if it was NASA. I think it was probably just NASA itself that just realized this, right? So they're tracking all of these objects. Some of these objects are old, defunct Soviet spy satellites. They are from a country that no longer exists, and so no one is making sure they're not causing damage anywhere, right? So they're just on their own orbit. They're not going to move out of the way. Fermi is a satellite that, is still operational, technically could move out of the way. Here's the problem. Fermi was not made to be able to do these sort of advanced maneuvers, right? There's some satellites that are really nimble and can kind of move and move around and things like that. All Fermi is supposed to do, it's just supposed to orbit and then tilt. It's supposed to just orbit around the Earth and kind of tilt up and look up at sometimes, look down sometimes, just do that to get its data. So with NASA, there's some law or some rule that if your satellite, right? So if your satellite at the end of its mission going to be deorbited, it's going to, it's going to slowly crash and burn, and it's going to hopefully burn up in orbit. If you have, if your satellite if there's a lot of dense enough material, it's not going to completely burn up in orbit, or in the atmosphere, which means you might get a large chunk of metal hurtling towards someone in Philadelphia, which is not great. You want to avoid hurtling large pieces of metal really fast from outer space into populated areas. So what they do is, if your satellite is heavy or massive enough, you have to have some way to control its deorbit. So what that means is, for a lot of these satellites, they will have a little bit of propellant. Not a lot of propellant, but a little bit, so that at the very end you can kind of control its orbit and crash it into the ocean. So you have a little bit of orbit, or you have a little propellant, but because it's only for deorbiting, it doesn't have to be that fine-tuned, right? And so what that means is there was all this propellant, liquid propellant, and the minimum amount of time you can open the tubes for that to release that propellant is 1 second. Now, 1 second of highly pressurized material going out will blast your satellite really far. And here's also another problem. It's pressurized in there. It's liquid. As soon as you open that gate, it's going to become gaseous, right? And everything will all of a sudden cool down really fast. And so there's always a possibility that when you try to close gate again, it's going to get stuck because now things have frozen. So this was the issue, 5, 10 years ago, where there was a question of this old defunct Soviet spy satellite and Fermi are going to occupy the same space, exactly the same space in the sky, I think like within a second of each other, or like tens of milliseconds of each other, right? And they're moving super fast. And so this is something this is one of the fun parts of being part of a space mission, is having to deal with things like this. And in the end, short story, everything was fine. But in the end, they did have to, there were a lot of these worries and sort of trying to figure out what to do. And so now at least we know that Fermi can survive and can release 1 second of propellant at once, and that's fine. And actually kind of helped. It kind of stabilized Fermi's orbit, right? So when it's shot, because of drag in the atmosphere, satellites are slowly deorbiting, right? They're slowly going to fall closer and closer to the Earth, and at some point they plunge in. So that's what Fermi's orbit was doing. It was getting lower and lower, and so because the liquid propellant was released, it kind of a boost, and that raised its orbit a little bit more. So now Fermi has time. It can keep spiraling for a lot longer. So that's part of the fun being on a space mission. Also fun is that you get issues like sometimes you have these solar panels, right? You have to do a lot of complicated things to try to figure out how do you get enough power but also not overheat your systems. There's this one gamma ray satellite, an Italian satellite called Agile. It was supposed to be similar to Fermi. It was supposed to sort of just kind of hang out and then look up and then look down, just kind of hang out and be very stable and look around and stuff. And And it turns out that right after launch, there are some parts of the internal machinery that helped it rock back and forth. Right after launch, some parts broke, and so it just started spinning. And so now to this day, we have this one satellite whose only mode is spinning mode, and it's just for tumbling and tumbling. But it can actually still do a lot of good science from it. So I think I'm done rambling. I don't have any more stories. Are there any more questions?
Question. So what's the lifespan for Fermi as we think of multi-messenger? So Fermi is still, well, it's already running budgeted amount of time. So what's the longest it could go?
Physically, I mean, so if you just leave it by itself, physically, it can last as long as the orbit is stable. The orbit's going to be stable for I don't know how long, but for at least decades, because there's really no consumables. So there's some satellites where you have to cryogenically freeze everything, or you have to lower the temperatures really low. Then that's a consumable, right? You run out of the cryogenic material, the temperature is going to heat up, and then you won't have your satellite anymore, or you won't have your telescope anymore. Maybe it degrades. Fermi, there's really no consumables on board. All the electronics, the solar panels are sufficient. We found different ways. The mission team found ways to sort of modify its orbit to kind of as a compromise for the stuck solar panel. So if you just leave it by itself, indefinite. The problem is politics. The problem is getting money from the government, right? So every couple of years, missions, so these big missions, every 2 or 3 years have to go back to the government and beg for more money, beg for another 2 or 3 year extension. They have to convince NASA headquarters that you should fund Fermi instead of all these other satellites. And it's a little tricky because you're all in the same category as Hubble and Chandra, which are these really enormous workhorses that everyone cares about, right? And so every couple of years you have to go back and say, this is new interesting science that you don't want to deorbit Fermi yet. And it helps that, with all these gravitational wave detection, it really helps. I mean, gravitational wave detections are great, but also within this framework, within this point of view, it's really detected gravitational waves because, like we've seen, Fermi GBM is really important for this multi-messenger science with gravitational waves, because it has the largest, because it sees the entire sky. There's no other gamma ray burst detector that sees the entire sky. So, sort of practical answer is forever, 30 years, but. Political answer depends on how much money they want to put in, or how long they want to keep funding Fermi. Because the problem is, as soon as the government or headquarters says we don't want to fund this mission anymore, you basically have to deorbit. I mean, not immediately, right? You have maybe 6 months or a year or 2 years to kind of, ramp down a little bit, but after that, you have to deorbit. You can't just let it stay up there because it's a large thing. You can't just let it hang out in the sky. So I think, yay, it's coffee break time. All right, see you guys after coffee break.